Hello, this is Dr. Fowler. In part 1, we talk about basic statistics and statistical analysis. In part 2 here, I want to talk about control chart for attribute. So just to recap, in part 1, we covered basic statistics, application of histogram, and normal distribution, standard normal, and control chart for variable, and we also talk about process capability index and how do we calculate that and understand what it means as it applies to quality of deliverable, whether it's design or customer requirements. So now we're going to talk about control chart for attributes. Attribute charts are used when we measure defects per unit of a product or number of defective units. If we are counting defects, then a unit may have multiple defects. If we are counting defective units, then a unit could be defective no matter how many defects is on it. So attribute chart are either we are counting defective units or we are counting number of defects per unit. These are the two types of control charts that we're going to talk about. So if we are counting defective units, we are normally using a P chart or an NP chart, which kind of represented by control limits as being the average defective plus or minus 3, again a standard deviation of the samples where we have calculated our average defective from. If the size of the sample is the same in all the samples, in other words, we're looking at the number of defectives in sample 1 that was 100 units, and another sample 2 that was also 100 units, and sample 3 that was 100 units, and so forth, then we are using an NP chart, which is essentially scaling the P chart to the size of n. And in that case, control limits will be n times P bar, if you compare that to P bar here, plus 3 standard deviation of the NP chart, which will be multiplying this part of the equation by n. So n goes under the bracket, under the square root function, and becomes np times 1 minus p, and this n will disappear. So both of these formulas for control limits are essentially the same. The difference is that this one is scaled by a factor of n, which is the size of the sample. So let's look at an example. Let's say that we are mass producing a product. The operator at various intervals take a sample of 50 units, inspect them, and record the number of defective units. So we have collected 15 samples of 50 units each. And then we calculate the control limits and plot a P chart. So the control limits now is P average plus or minus 3 standard deviation. And for this proportion defective, for number of defective per sample, the upper control limit is 0.3024, and in other words, you calculate I'm going to show the sample, and the lower control limit is 0. Let's look at the data here. So I had 15 samples of 50 each, and the first one had 10 defective, the second one had 10 defective, the third one had 9 defective, and the fifth one had only 4 defectives, and so for the last one had 9 defectives. So if because the sample was 50, I can calculate the percent defective of this sample. That will be 0.2, 0.18, and so I'm getting the percent defective or the fraction defective on each of the samples, and if I average it, then I get my P bar. And so the control limits, then the upper control limit will be the P bar plus 3 times P bar times 1 minus P bar divided by 15, which is my sample size, and that, as showed in the previous slide, is 0.3024 for upper control limit, and the lower control limit is negative, as we talked about in the previous video. Whenever the lower control limit is calculated as a negative value, we put it to 0. And so now I've got my upper control limit, lower control limit, and the center line, or this is the lower control limit, and this was the center line. And so now I can plot that. Here's my P chart. The upper control limit, the lower control limit put at 0, and these are the P bars that I calculated from each sample, the proportion defective. And we plot this along the center line. This was the P bar line. And we look at it again, just like any other control limit. Are these data points randomly distributed around the mean? And are they within the control limits, so that we can say the process is in control and stable? If the point doesn't look like it is randomly distributed, then we can see there is a special cause or some instability, and we're going to need to investigate to see how the process is being affected. So now, since that my previous data set was actually a fixed sample of 50, I could also plot that as an NP chart. So for an NP chart, then the equation is multiplied by n, which in this case was 50. So n times P bar plus and minus 3 standard deviation. And if we multiply then this equation, by 50, we're going to get 50 times really essentially what I had before. Is the limit was in the P chart was 0.3024. When you multiply by 50, it becomes 15.122, and the lower control limit again end up being 0, and the average defective in this case now will be 7.533. Now you can calculate it two ways. One, you get the P bar multiplied by 50, or you can actually calculate it from the previous data set that we had here. If these were the number of defectives, if we average this number, we get that the same value that I had there as 7.533. And so when we plot this center line, upper control limit, lower control limit, we get essentially the same control chart, except that here the control limits are multiplied by n. The same thing with the center line, as well as the data point. Now these are not the fractions, but these are the actual number of defects. So the first sample had 10 defects, the second one had 10 defects, the third one had 9, and so forth. But you could see the shape of the distribution. The control here, or trend line, is the same as we had before, and we can again claim that this process is in control and perhaps is stable as well. We can really argue that many of these points are affected by an external process. So that was when we are calculating proportion defective. How many of our units are defective as we sample them. That was P chart and NP chart. If we are counting the number of defects on a unit as it comes out of production, or however we are producing it, then we are talking about the number of defects per unit. In this case, we are using a slightly different control chart. We use C chart and U chart, used for measuring defects per unit. Now C chart is used, the control limit again is a C bar plus or minus 3 standard deviation, which in this case the C bar is the average number of defects per unit. So in the case of C, all the units are the same. Think about it. For example, if we are looking at scratches on a automobile model coming off the production line, they're all the same car we're looking at, and then we count how many scratches on this one, how many scratches on the next one, and so forth. So we're counting the number of scratches or number of other defects that the car may have, and so for that we're using a C chart. And so that will be a question for C chart. On the other hand, if you're looking at the at a product that have those samples are different sizes. Let's say that we're looking at production of glass, panels, and there are different sizes, and you're looking at the imperfection from that. Or in IT, if you're looking at the number of defects in a module, and so the modules are different size, but the number of defects will represent how many lines of code are wrong or has problem. So in that case, we're counting defects we're going to calculate it per average unit, because the units are all of different sizes. In that case, we're using a U chart. And so again, the formula is very similar, except that here we're using the U bar divided by N to get essentially an average N. So let's look at an example. I talked about the car, so let's say that we are checking the cars for the number of defects on the car as they're coming off the production line. So this is car number 1, 2, all the way to number 10. And the first one had 14 defects, 13, 26, 15, all the way to last one 13. So the total number of defects is 170. The number of units of car that we looked at it is 10. So if we then are adding 170, dividing it by 10, we get the average number of defects per unit, right? So that will be 17 defects per unit, and all the units are all of the same size. So my control limits, the upper control limit then is C bar plus 3 square root of C bar, this missing a bar, and that will be 17 plus 3 times the square root of 17, end up being 29.36. That's upper control limit for defective, whatever the defects we're measuring in the car. And the lower control limit will be C bar minus 3 square root of C bar, and that would be 4.64. So here we had, in the vertical column, I put all those defects per unit. And this is my C bar, this is upper control limit, this is lower control limit, and so now I can plot the control chart. This is for defective cars as they come in. We don't care how many defects it has, but as long as it has one defect on it, it's a defective car. And so as we plot, we can see the number of defects per unit, and as long as they are within the control limits, as we have calculated, then we say this process is in control, and in this case actually stable. Again, to understand, we probably don't like any defects on the car, but our process of perhaps if we're looking at the painting, our process have some inherent variation, and it's going to generate some defects, and based on that inherent variation, there is a control limit of how many defects the process will create. Now, if this control limit represents what's acceptable to our customers, then the cars are okay, and they can be, put in a lot and sell them for those few number of the scratches that we have. On the other hand, if it's not acceptable, then we have to fix those defects or reject them they're not going to be accepted at the final inspection, and they need to go back and rework on it. That's how the notion of a P chart. The defective units are either totally rejected if it doesn't work. For example, if that had something to do with the operation of the vehicle and it could not work, then it will be totally rejected, or it goes back and get repaired and then put back into the process. That's the notion of defective units. Okay, now let's talk about the U chart. Now here is when we're measuring the number of defects per unit when the units are not the same. So I'll talk about IT or software. Say that I've got 15 modules of different sizes, 16,000 lines of code for the 300, and so forth. And then as we do inspection of the code, we find out that there were 3 defective lines of code in the first module, 16 in the second, and so forth. So I'm getting the number of defects per module, while the modules are of different sizes. To use the control chart, now we have to define a standard unit to measure all the modules by that. So I'm going to define 1,000 lines of code as to be my standard unit that I'm going to use. So the first module is 6,000 lines of code, so it is 6 standard unit. This is 4,300, that's 4.3, 2,900, and so forth. So I'm getting the number of standard unit per module in here, and the total of that is 59.5. And then I'm going to get the number of defects rate per standard unit. So here I had 13 defects and I've got 6 units. So 13 divided by 6 gives me a defect rate of 2.167. For the second module, I'm getting 3.721. For the third, 2.414, and so forth. So I'm getting the defect rates, which will be the C divided by N in this column. And then if I average that, I'm getting my U bar as 3.276. But I also need to find, because each module has a different number of units, I need to calculate the average number of units per module. And that will be taking all of these units, which is 59.5, and dividing it by 15. And so that I've shown here, that we call that N bar. That's the average unit, number of units per module. Okay, so now I've got my N bar, and I got the U bar and N bar, so I can calculate my control limit. Upper control limit is N bar plus 3 square root of U bar divided by N bar, that is 6. And the lower control limit is U bar minus 3 square root of U bar divided by N bar, that's 0.549. And now I can plot my control limits. So I've got upper control limit, lower control limit, and this average of the U bar, and here I'm plotting the number of defects per unit, per standard unit in each of the modules, and I'm plotting them here. And you can see from the chart that this process is under control and is stable. The data points are randomly distributed around the mean, and none of them is going outside the control limit. So that will be looking at the process and saying that our development process or coding process is in control, and that's the level of defect that will generate. Now, if this level of defect is not acceptable, then we may need to do more training and improve. And if we improve the process, then these control limits will shrink and become tighter, and that may be what the customer may want to require from us to produce in terms of the quality of the output. So that's how we look at the U chart. Now with that, let me just summarize. So we talked about control chart for defective units and control chart for number of defects per unit. In the case of defective units, if the sample size, like we talk about production of various product or gadget, if the sample size each time is the same, then we can use an NP chart. If they're different, we can use a P chart. And we showed how to calculate the control limits. If, on the other hand, we are measuring defects per unit, as I talk about it, for example, in the scratches coming off the car, then we said we're going to use a C chart to look at each car. All these units are the same in this case, and then see how many defects are per unit, and see whether our process is in control, and also whether or not the output is acceptable. On the other hand, if the module or the unit that we are inspecting are of different sizes, this will not apply to cars, because if you're thinking about two different model cars, you can't say how many standard unit is in one versus the other. But if you were producing, as I pointed in the example, lines of code, so we have got modules of lines of code of different sizes, or if you're producing let's say that sheets of aluminum, so they will be of different sizes, but essentially you can calculate the number of units within each. Those units will be all the same measure, there may be a square foot. Then we can use a U chart and see the average rate of defects per unit and see whether or not the process is in control. And I illustrated both of these control chart with examples. So thank you for watching, And this was the last slide of this module.